Hello, my name is Tom Spink, and today I'm going to be talking to you about ISA Paravirtualisation. So let's start by breaking apart the title of this talk, and the first part is ISA. What is ISA? ISA is an instruction set architecture. Machine code, data types, registers, memory, all of these sort of things go to make up the instruction set architecture. And paravirtualization? Well, related to virtualization, paravirtualization means I know I'm being virtualized. And if you know you're being virtualized, then you have the opportunity to maybe make some operations more efficient. Instead of having to emulate every single little thing, if you're being paravirtualized, you can say, oh, well, I know that I'm being paravirtualized, so why don't you just give me that resource directly? So, what is instruction set virtualization? Well, this is running a program that's written in one ISA on another. For example, an AArch64 guest program running on an x86 host machine. And there are a couple of techniques that we can use to do instruction set virtualization. One of the most easiest techniques is interpretation, but it's quite slow. So this is where you just look at each instruction as it's being executed, each guest instruction, and then call a function to emulate that instruction. So its interpretation is slow, but it's very easy to implement. A better technique is dynamic binary translation, or DBT. DBT is much faster because you're taking sequences of guest instructions and turning them into sequences of host instructions. So it's super fast, it's very fast, but it is hard. There's lots of things that you need to take into account when doing DBT, and you have to build JIT compilers and all sorts of things in order to get the most benefit out of it. And there are loads of different types of instruction set virtualizers and different existing programs that do this. So there's QEMU, which you might be quite familiar with. There's Rosetta, which is something from Apple. There's ArchSim and Captive, which has come out of our research groups, and Gem5, which is another research-oriented instruction set virtualization engine, or you could call it a simulator. Now, Rosetta version 2, Apple are doing this. Binary translation. So they've switched architectures again. They've gone from an Intel architecture to an ARM architecture, their own internal ARM architecture, and they want to support transitional code. So they want applications that have been written for the Intel architecture to keep working on their ARM machines whilst application developers keep up and they build universal binaries that contain both Intel and ARM instructions. Now, they make it clear that Rosetta isn't really geared towards legacy code and supporting legacy code, but is really just there as an assistance when transitioning from x86 to ARM. Now, Apple is a big company and they're doing this for real, but there's a number of limitations or restrictions that are imposed by the Rosetta DBT. Very minimal information about it, but what we can find out is that you cannot switch between architectures. It's either one or the other. So either you take an Intel binary and you run it in translated mode, or you run exclusively in ARM mode. The majority of it is ahead of time, although it does have support for doing JavaScript stuff. But because it's ahead of time, there's a large startup latency. So if you have an Intel binary that you want to run, quite a lot of translation is done when you start up that program, leading to this great startup latency because the translation has to happen. And there's also sort of architectural restrictions, like it doesn't support AVX instructions, and certainly none of the system style instructions, such as virtual machine monitors or anything like that. Now, what is instruction set paravirtualization then? So we've spoken about instruction set virtualization. What is instruction set paravirtualization? This is where you run a program written on one ISA on another, for example, an AArch64 guest program on an x86 host machine, just like before, but this time the program knows that it's being virtualized, or at least the runtime knows that something is going on here. And what's the actual problem we're trying to solve then? How does this actually... Where is the issue? Well, we've said that DBT is fast, but it still does introduce some overhead. Doing dynamic binary translation is not as quick as running natively, and that's because, well, DBT involves this translation phase where you discover the code that you're executing, you turn it into host machine instructions, and then you execute it. So there's sort of latency from that translation, but there's also overheads introduced in the generated code as well, because the translated code isn't going to be as optimal as natively compiled code, and there'll also be overhead from the actual DBT runtime itself. So what if we could actually use some already existing native code instead of translating guest code? So the key idea here is to use host code directly instead of translating if it's available. And a way that we might implement this is through using shared libraries. So let me come on to that point just now. This is how shared libraries generally work. If you look up in the top right hand side of the diagram here, number one is to load the main program binary. So when you execute your program on your operating system, the main program binary is loaded, and then the loader sees that there is an interpreter associated with it. And that interpreter is nothing to do with instruction set virtualization. It's nothing to do with simulation. It's called the binary interpreter. And that interpreter is actually the dynamic linker or loader, which is normally ld-linux.iso on a Linux platform. So once the ELF binary has been loaded, the interpreter has been resolved, and then the interpreter is loaded, or the dynamic linker or loader is loaded. The dynamic linker and loader analyzes the ELF binary, figures out what the shared library dependencies are, creates an internal mapping of those, and then just prepares and starts to execute the main program. And then execution continues in the main program until number 4 here, the program calls into a shared library. So at this point, when a shared library call is made, it hooks back into the dynamic loader, which then resolves the symbols, makes sure that the shared library is loaded and ready to go, and then passes execution into the shared library. Execution at number 6 then happens in the shared library, and once the shared library has finished, it returns back into the main program, and the main program continues. And then, if you've seen point number 8 over here, the call is actually cached, so that next time you call into the shared library, provided it's a function that you've seen before, it just runs directly in the shared library. The dynamic linker doesn't need to be involved anymore. Now, how do we do dynamic binary translation on a binary that uses shared libraries? Well, all we do is we take that diagram from the previous slide, a big diagram, we squash it down and stick it in this translated code bucket. And what that means is that actually the virtualization runtime, so QEMU or whatever, will just execute all of that as translated code. So you'll have a guest ELF binary, you'll have a guest dynamic loader, and you'll have a guest shared library. And then all will be translated, everything. So your DBT might be ARch64 on an x86 host machine, so you have an x86 virtualization runtime, but all of your guest programs, everything from the binary, the loader, and the shared library will all be ARch64 code. Okay, so that's how dynamic binary translation works with shared libraries, and that's QEMU's approach to doing this. At a bit of a higher level, you can see here that the translated code really does comprise of just ARch64 binaries, the loader, and all of the shared libraries. So now here's this idea again. What if we can use host versions of these shared libraries? So already compiled existing code for the host architecture. And what we end up getting is a sort of a mirroring of these shared libraries. So we have the guest versions of the shared libraries, which mirror the host versions of the shared libraries. The only difference is that the guest versions are obviously compiled for the guest architecture, in this example ARch64, and the host versions are compiled for the host architecture, in this example x86. Now, here's the idea. When we detect a call to a shared library, call the host machine's version instead. Seems pretty straightforward. Why aren't people doing this already? Well, we'll get to the challenges in a minute. But all we have to do is when we're executing the ELF binary, so this is translated code, and the ELF binary makes a call into a shared library, normally we would just translate the dynamic linker and loader and then run those internal routines. But instead, if we detect this call into the shared library, pass execution onto the host shared library, and once that completes, return back into guest machine execution. Okay. So what are these challenges then? Well, the first challenge is how we actually detect a call to a shared library. We could do something clever like using LD preload in the guest, but this requires a stub to do a hypercall. So that particular approach involves writing a shared library that intercepts the symbols of existing shared libraries. And then those intercepted symbols are just stub functions that then tell the virtualization runtime to call into the host native library, which is sometimes termed a hypercall. So we can do that. We can say LD preload this stub library. The stub library will intercept a function, and it will do a hypercall in the main application, in the virtualization runtime, which will then call the native code. Another approach is to do DBT instrumentation. Well, we're already running in a DBT context, which means we know what code we're translating. So instead, if we make the DBT aware that a shared library call is happening when the program branches to a particular address, then we can handle this transparently without having to use stub functions. We can just detect that we're calling that address and instead pass it straight onto the native library rather than doing the translated library. So there are a couple of ways of detecting shared library calls in guest programs. But now the bigger challenge is actually how do we marshal this call between the guest machine and the host machine? The guest library is, the guest program is written with the particular guest's ABI in mind, so the ARch64 ABI, for example. And the host library is using the host machine's ABI, the system V ABI. So how do we actually pass parameters between these functions? How do we put parameters in and get return values out? These are defined by the ABI, or the application binary interface. So we need to know what those ABIs are. We need to know the guest ABI, we need to know the host ABI, and we need to translate between them at the call boundary. But interestingly, it's not just enough to get the right values in the right registers. You can't just put argument 0 in the correct register and think you're done with it. We actually have to consider the semantics of those parameters as well. What if the parameter is a memory? What if the parameter is a file descriptor? Or even worse, what if the parameter is a function pointer? How on earth do we handle that? If it's a file descriptor, the guest machine has this virtualized view of what file descriptors are. So what it thinks is file descriptor 7 might not be what the host thinks is file descriptor 7. So we need to know that that parameter, which is normally just an integer, is actually a file descriptor under the hood so that we can translate between it. And for function pointers, say we have a sorting function that takes a function pointer as the callback for the comparison instruction, for example, quicksort. How on earth do we handle that? The guest program is going to pass in a guest address function to the host library code. Not a chance will the host library code be able to call that guest function because, well, it's in the guest ISA. So we need to insert some kind of thunk to translate between these two things and actually make that happen. In order to support this, we're going to need some sort of interface description language, or an IDL. We need to describe the functions that we want to paravirtualize and say what the semantics, what their arguments look like and what the semantics of those arguments are. And how do we support exceptions and signals? If native code throws a signal or throws an exception, how do we actually propagate that back through to the translated guest machine? Another question is how we actually manage the resources between the guest and the host, and in particular this will be memory. If guest has allocated memory, how do we make sure that the host has access to that at the right point? And likewise, if host allocates memory, how do we make sure that the guest has access to that? Is it even compatible to be able to allocate and free memory on different sides, or do we need to make sure that memory that is allocated and is freed on the guest, and memory that is allocated is freed on the host? And what about full system simulation? I'm actually only talking about user mode simulation here, or user mode virtualization, where it's one application that's being run through DBT. Can we support this for full system? And what does that actually look like? Does it look similar, or is it different? How do we support it? And is it worth it? Is it worth it to do any of this? Well, let me show you this graph. Here are some initial results from a floating point micro benchmark. So one of the things about QEMU is that QEMU has a software floating point implementation, which means any floating point operation gets translated to a call instruction, which goes into a helper function that does the floating point operation. So I've implemented all of these ideas into QEMU, and I've run this floating point micro benchmark to see the speed up. Because if you have a function, if you're using the math shared library, and you have a function such as sine or cos or tan, and you call that in your program, you're actually calling into a shared library, the maths library, to do that particular function. And so here, what we can see is we can see a speed up, because instead of this shared library being translated inside the guest machine and executing translated code and then going through QEMU software floating point mechanism, instead, when we call the sine function, we are calling the host machine's native version of that sine function, optimized for the host machine. So we're calling it directly from the guest application. Now, in this example, we have an ARch64 guest machine and an x86 host machine. And you can see that pretty much most of the benchmarks here are on the one line, which means there's no change. And that's because plus, minus, multiply, divide, and square root, they don't involve function calls. But sine, cos, tan, arcsine, arccos, and arctan, exponentiation, and logarithm, they are all function calls. And we're intercepting at the function call level here. So when we see in the guest application a function call to the sine function in the math library, we call the native version of that function directly instead of translating the guest function. So we can see here that paravirtualizing just a few functions from libm.so leads to these speedups that we can see in this micro benchmark. And then this does actually apply to real world benchmarks as well. I'm currently in the process of running these benchmarks, but for example, the Parsec Black Skulls benchmark achieves a 1.52 times speed up just from paravirtualizing the exp and log functions from the math library. So just by adding those two functions into the paravirtualization step, we can get a 1.52x speed up on the benchmark. So where do we go from here? What is next? Well, of course, it's to port more libraries and functions. I want to run more benchmarks. I want to support more function styles or different semantics of parameter passing. So more functions from glibc. And interestingly, OpenCV as well. I want to be able to support that. We need to solve some additional marshalling challenges. So I spoke about function pointers being a particular challenge. I haven't actually solved that yet, but it's definitely in the pipeline. I also need to investigate what the behavior of signals are in this context as well. They might just work. My intuition tells me that only a little bit of modification will need to be done to propagate signals properly. So I'm quite hopeful about that. And then we're going to submit a paper all about this. So that's what we're going to do. And then sort of future directions here, it's identifying how we can do something like this for full system simulation. What does it look like for full system simulation? What does it mean to do paravirtualization in a full system context? Thank you very much for listening to my talk. If you have any questions, please send me an email about them since you'll be watching this offline.